We always hear that AI needs perfect data to learn anything, right? Clean, pristine information. But what if that's not true? What if an AI could learn something as incredibly delicate as surgery by watching us with all our human imperfections? Yeah, let's get into it. Okay, just picture this for a second. A really complex surgery, deep inside your body, but without a single cut. No scalpels, no big incisions. Sounds like something straight out of a movie, right? Well, it's the future that some really groundbreaking tech is aiming for. And to make it a reality, to automate it, we're going to need a whole new way of thinking about AI. So this incredible technology is called magnetic actuation. And the core idea is, well, it's one of those things that's so simple, it's brilliant. Instead of cutting a patient open, you use powerful magnets on the outside of the body to steer these tiny, untethered surgical tools around on the inside. So how does that even work? Well, you've got this robotic arm moving a big magnet around. That's the external permanent magnet, or EPM. And the magnetic field it creates, it lets you control this tiny little magnet, the IPM, that's attached to a surgical guide wire, navigating, say, a patient's blood vessels. It is literally remote control surgery, but on a microscopic scale. Pretty wild. All right, so we've got this amazing hardware. The next big question is, obviously, how do we automate it? And the most common way to do that is something called learning from demonstration. You just have an AI watch a human expert do their thing and learn. Simple, right? Well, there's a huge catch. Humans, we aren't perfect machines. And this slide just nails the problem perfectly. Look at the left side. That's the ideal world, right? A smooth, perfect, error-free path. That's the kind of data an AI would just gobble up. But then you look at the right. That's the real world. That's a human expert. You see the little hesitations, the tiny corrections, those moments where the control isn't absolutely flawless? That, my friends, is what the researchers call noisy data. And look, this isn't just some small hiccup. The researchers behind this paper basically say this is the problem. Collecting perfect demonstrations, it's really, really hard. In the real world, noisy data is what you get. It's the norm. So if you're trying to build an AI that actually works in our messy reality, you have to figure this out. So, just how messy are we talking? Get this. In the data they collected for this exact experiment, about 37% of the movements recorded from the experts were flagged as invalid, or, just not great. Over a third of the examples were flawed. I love this analogy. Trying to teach an AI with that data is like trying to learn a new language from a textbook where a third of the sentences are just plain wrong. How could you possibly succeed? So what do? The obvious answer might be, well, just clean up the data. But that's super expensive and takes forever. The real aha moment here wasn't about fixing the data. It was about building an AI that was smart enough to learn from the mess itself. And their solution has a name, the adaptive sampling policy. The easiest way to think about it is like having two AIs. You've got your main student AI, the one trying to learn the surgery, and then you have a second tutor AI. The tutor's only job is to watch the student train, figure out which examples are the trickiest or the most useful, and then tell the student, hey, pay extra attention to these ones. And this analogy is just perfect. Normal AI training is like a student who just rereads the entire textbook page by page, including all the typos and wrong answers again and again. But this new approach, it's like a smart student who takes a practice test, sees they bombed a certain chapter, and then focuses all their energy on that one chapter. It's just a much, much smarter way to learn. So let's walk through how this smart feedback loop actually works. Step 1, the student AI takes a crack at learning from a batch of data. Step 2, it figures out which of those examples were the hardest for it to understand. Step 3, it sends that report back to the tutor AI. And then Step 4, the tutor sifts through all the messy data and handpicks a new batch of examples specifically to target the student's weak spots. And they just keep doing this over and over, getting smarter with every single cycle. Okay, it's a really cool idea on paper. A smart tutor for an AI. I mean, it makes sense. But the billion-dollar question is, does it actually work in the real world? Well, let's check out the results. First up, they ran some simulations. They took 3 totally different, top-of-the-line AI learning methods. The middle column there shows you how they did with the standard read the whole textbook method. And the column on the right, that's how they performed with our new smart tutor guiding them. It's a clean sweep. Across the board, every single algorithm got a serious performance boost. No question about it. But hey, simulations are one thing, right? The real test, the real challenge was way tougher. They did something called a zero-shot deployment. Now, what that means is they trained the AI on a ridiculously small and messy dataset. We're talking just 20 human demonstrations. And then they just let it loose on the real robotic system. No practice runs, no do-overs. This is as high stakes as it gets. So, the moment of truth. How'd it do? Well, let's start with speed. The AI that was trained the old way took about 46 seconds to complete the surgical task. Not bad. But the AI that had the smart tutor, it breezed through it in just 39.5 seconds. That's a full 6.5 seconds faster. Now that might not sound like a lot, but in a delicate surgery, that is a huge difference. It's proof that the AI didn't just copy what it saw. It actually learned a smarter, more efficient way to do the job, all from the same imperfect examples. And get this, it wasn't just faster, it was actually safer and more reliable too. The smart AI had a more than 5% increase in valid steps, which is just a technical way of saying it was much better at keeping precise control over the tool. So the big takeaway here is that it's faster and more stable. It's a win-win. Okay, so this is obviously amazing for this one surgical robot, but we need to zoom out because the implications here are way, way bigger than just this one lab. This research is basically a roadmap for a totally new, much more efficient way to teach AI how to do things in the real physical world. So what's the big picture here? It means we might not need these gigantic, perfectly curated datasets to teach robots how to do really complex stuff. And that makes it so much easier and cheaper to automate expert-level tasks. We're not just talking about surgery anymore. Think about advanced manufacturing or deep-sea exploration, really any field that relies on a human expert's skill. This is a huge step toward building AI that can learn from our messy reality, not just from some clean, perfect fantasy. And that leaves us with one last really mind-bending question to chew on. For so long, we've thought of our human mistakes, our imperfections, as a problem, something that contaminates the data for AI. But what if that's wrong? What if an AI can learn from our imperfections to become even better, even more efficient? If that's true, what other impossible skills are suddenly not so impossible anymore?